Every human alive today, all 8 billion, descends from a population that at one point numbered fewer than 10,000 individuals, possibly fewer than 3,000, a breeding population smaller than the student body of a typical American high school. Geneticists call this the human genetic bottleneck. For decades, they could measure it. See it written in mitochondrial DNA and Y chromosome sequences, but couldn't explain the cause. The genetic signature was unambiguous. Sometime around 70,000 years ago, something killed almost everyone. Then a geologist in Sumatra found a layer of ash. The same ash appeared in ice cores from Greenland, ocean sediment from the floor of the Indian Ocean, and soil excavations across South Asia, East Africa, and the South China Sea, all at the same depth, all dating to exactly 74,000 years ago. Chemical fingerprinting proved every sample came from one source, a single eruption in what is now Indonesia. The eruption ejected 2,800 cubic kilometers of material, enough to bury the entire Indian subcontinent under 15 feet of ash. The sulfur dioxide it injected into the stratosphere blocked sufficient sunlight to drop global temperatures by 3 to 5 degrees Celsius for 6 years. Forests died. Food chains collapsed. The human population contracted to a handful of survivors in scattered refuge zones where conditions remained barely survivable. A volcano that nearly ended the human species left its evidence in every living person's DNA. The investigation began in ice. In the 1990s, climatologists drilling cores from the Greenland ice sheet found a distinct layer of volcanic ash dating to approximately 74,000 years ago. Ash in ice cores isn't unusual. Volcanoes erupt, debris drifts, it settles in polar ice and gets preserved as a thin gray band. But this layer's chemical composition didn't match any volcanic source in the northern hemisphere. Marine geologists then found the same ash in sediment cores from the floor of the Indian Ocean. Same chemical signature, same date. Archaeologists excavating sites in India found it buried in soil, not a thin dusting, but deposits measuring 4.5 meters deep in some locations. 15 feet of volcanic ash sitting directly on top of what had been inhabited land. The ash became a global timestamp. It appeared in cores from the South China Sea, sediment from East Africa, deposits across Southeast Asia. Every sample, when analyzed, revealed the same mineralogical fingerprint: high silica content, specific isotope ratios, trace element concentrations matching only one location on Earth, Toba, a caldera in northern Sumatra. The word caldera undersells what Toba is. It is not a crater, not a bowl-shaped depression from an impact. It is a collapsed magma chamber, a wound in the Earth's crust approximately 100 kilometers long and 30 kilometers wide, now filled with water to form Lake Toba, one of the deepest volcanic lakes in the world. The lake sits 900 meters above sea level, surrounded by steep walls that mark where the ground fell inward when the magma chamber emptied 74,000 years ago. The depth of the lake, 450 meters in places, gives a measure of how much volume the eruption excavated from the crust beneath. Archaeological sites in India show the ash layer as a dividing line. Below it, stone tools, fire pits, faunal remains. The record of continuous human occupation extending back tens of thousands of years. Above it, nothing for thousands of years. The tools stop, the fires stop, the record goes silent. The ash documents an event so large it distributed identifiable debris across multiple continents and erased the human record across an entire hemisphere in a single geological moment. The silence above the ash layer is not absence of evidence, it is evidence of absence. Toba is not a mountain. It was never a mountain. This distinction matters because our mental image of volcanoes, the cone-shaped peaks in textbooks, describes a fundamentally different type of system. Supervolcanoes form when massive magma chambers accumulate beneath the crust over hundreds of thousands of years. The magma doesn't build upward into a peak. It pools horizontally, creating pressurized reservoirs measuring thousands of cubic kilometers. The crust above becomes a stressed roof, increasingly fractured as the chamber swells. When the roof fails, the collapse is structural. The ground falls inward while the chamber's contents decompress violently upward through the failing crust. The result is not an eruption in the conventional sense. It is simultaneous collapse and decompression across a surface area measured in thousands of square kilometers. Toba's magma chamber held approximately 2,800 cubic kilometers of material at the time of the eruption. The caldera that formed measures 100 kilometers long and 30 kilometers wide. Placed over the San Francisco Bay Area, it would stretch from San Jose to Sacramento. The Volcanic Explosivity Index, VEI, measures eruptions on a logarithmic scale from 0 to 8, each step representing a tenfold increase in ejected material. VEI 8 is the maximum category, eruptions ejecting more than 1,000 cubic kilometers. Toba was VEI 8. Mount St. Helens in 1980 was VEI 5, ejecting approximately 1 cubic kilometer. Krakatoa in 1883, an eruption heard 3,000 miles away that killed 36,000 people, was VEI 6, ejecting roughly 25 cubic kilometers. Toba ejected 140 times Krakatoa's volume. This wasn't an anomaly in Toba's history. Geological surveys document at least 2 prior supereruptions, one approximately 840,000 years ago, another around 501,000 years ago. Each left collapsed calderas, ash deposits, and geochemical signatures in the regional record. The intervals between eruptions span roughly 300,000 to 400,000 years, the time required for the magma chamber to refill and repressurize to the structural failure threshold. Toba operates on a cycle, and the cycle is ongoing. The lake occupying the caldera today is deceptive. In its center sits Samosir Island, nearly the size of Singapore, a resurgent dome, a section of the caldera floor pushed upward by magma refilling the chamber below. The dome rises because pressure is building, not imminently. The intervals between Toba's supereruptions span hundreds of millennia, but small earthquakes register regularly in the region. Hot springs vent gases along the shoreline. Monitoring stations track ground deformation indicating ongoing magma movement. Toba is dormant. The geological process that produced 3 prior VEI 8 eruptions has not stopped. The magma rises, accumulates, and waits. When the roof failed 74,000 years ago, the eruption column reached the stratosphere within hours, traveling at speeds exceeding 100 meters per second. The column punched through the troposphere, the layer of atmosphere where weather occurs, where clouds form and rain falls, and entered the stratosphere, where the air is thin, stable, and does not mix vertically with lower layers. Materials that reach the stratosphere don't fall the way ash falls in the troposphere. They spread horizontally, carried by high-altitude winds circulating from equator to poles, distributing globally over weeks and months. The ash descended relatively quickly. Once above the troposphere it settled, within days to weeks depending on particle size and distance from the source. The sulfur dioxide did not. It remained suspended, undergoing chemical transformation that would alter the atmosphere for years. The immediate kill zone extended hundreds of kilometers from the caldera. Pyroclastic flows, ground-hugging avalanches of superheated gas and pulverized rock, reaching speeds exceeding 200 kilometers per hour and temperatures above 700 degrees Celsius, sterilized Sumatra and surrounding regions within hours. Pyroclastic flows don't char organic matter. They vaporize it. Trees, animals, soil structure, gone within seconds of contact. The long-range destruction traveled not across the ground but through the air. Ash from Toba reached the Indian subcontinent within days, accumulating continuously at rates that buried vegetation faster than ecosystems could respond. In parts of central India, deposit layers measure 4.5 meters thick, 15 feet of compacted volcanic debris sitting on what had been forests, grasslands, and river valleys. The ash wasn't inert. Volcanic ash consists of tiny glass shards, fragments of magma that solidified explosively when exposed to air. Each particle is a jagged splinter. Inhaled, these particles don't dissolve or break down in lung tissue. They lodge in airways, causing progressive respiratory failure. Large animals, elephants, rhinoceros, large predators, died not from fire but from suffocation, their lungs shredded and clogged by the very air they breathed. Smaller animals with proportionally larger surface area relative to lung capacity died faster. The ash fall killed through the respiratory system first, across every animal that couldn't shelter from the air itself. The ash also contained fluorine and other soluble toxins leached from the volcanic rock during the eruption. When the ash fell on vegetation, rainfall dissolved these compounds into plants, poisoning herbivores that fed on contaminated leaves and grasses. The toxins bioaccumulated, herbivores concentrating fluorine in their tissues, predators concentrating it further by consuming multiple contaminated prey animals. Rivers turned gray, choked with suspended volcanic sediment that made water toxic without killing thirst. Animals that approached water sources for relief found contamination. The food web was poisoned at every entry point simultaneously: air, water, vegetation, and prey. Archaeological evidence documents the human collapse precisely. Excavations across South and Southeast Asia reveal the same pattern: occupation layers containing tools, fire pits, and faunal remains terminate at the ash layer. Above it, nothing for thousands of years. Tool-making traditions that had persisted for millennia stop. The humans who carried those technologies either died or fled and never returned. The groups present when the ash fell faced a situation with no viable response. There was no higher ground when the danger arrived from above. The ash fell for weeks. Even after it stopped, the contamination persisted across the landscape. Food sources were buried or poisoned. Water sources were toxic. Some groups sheltered in caves. Ash intrusion into cave deposits at several Indian sites confirms humans were present when it arrived. But caves provide no food and don't filter air. Without uncontaminated food and water, survival in place was not possible for more than days. Some groups attempted migration, moving through a landscape actively being buried under feet of contaminated material. The ash would have made direction finding difficult. Landmarks buried, river channels choked and altered, the horizon obscured by suspended particles. Moving through ash of this depth is physically exhausting. Each step sinks into unstable material. Breathing requires effort against a particulate-laden atmosphere. Animals that might have been hunted for food were either dead or had fled. The landscape was actively hostile to movement at the moment movement was the only option. Most people died where they stood, their bodies compressed over millennia into the sterile gray layer that now marks the boundary between before and after in the South Asian record. The ash fell first. The sulfur dioxide lasted years. The eruption injected an estimated 5 billion tons of sulfur dioxide into the stratosphere. At stratospheric altitudes, sulfur dioxide reacts with water vapor to form sulfate aerosol particles less than 1 micrometer in diameter. Particles this small have negligible settling velocity. Air resistance relative to mass is too great for gravity to overcome at normal stratospheric conditions. They remain suspended, distributed by high-altitude winds across every latitude simultaneously. Unlike ash, which fell heaviest near the source and thinned with distance, the aerosol layer spread uniformly across the entire planet within months. A uniform global veil, not a regional blanket. The aerosols reflected incoming solar radiation back into space before it reached the surface. Shortwave light from the sun, the wavelengths that drive photosynthesis and warm the ground, struck the aerosol particles and scattered back into space. Ice core data from Greenland and Antarctica confirm global distribution. Both show sharp sulfate concentration spikes coinciding with the Toba eruption date. Climate proxies, oxygen isotope ratios in cave formations, growth rings in ancient wood, pollen records from lake sediments, all record the same signal. A sustained temperature drop beginning 74,000 years ago, appearing simultaneously in records from every continent. The magnitude remains debated. Early models suggested drops of 10 to 15 degrees Celsius regionally. More recent models using better aerosol data estimate global average reductions of 3 to 5 degrees Celsius sustained for approximately 6 years, with regional variation. 3 to 5 degrees over 6 years. The difference between today's climate and the last glacial maximum, when ice sheets covered Canada and northern Europe, is approximately 5 to 6 degrees globally. Toba compressed a glacial-scale temperature shift into a span of years, not millennia. Growing seasons collapsed. Plants require specific temperature thresholds for germination, growth, and reproduction. A multi-year reduction of 3 to 5 degrees shifts those thresholds beyond viable ranges for many species in temperate and tropical zones. Photosynthesis rates dropped as aerosols absorbed the shorter wavelengths plants use most efficiently for converting sunlight to chemical energy. Plants that survived the initial ashfall but depended on annual reproductive cycles failed to produce seeds, meaning their recovery in the following season depended on those seeds, which didn't exist. Perennial species survived longer, but showed dramatically reduced growth rates visible today as narrow rings in ancient wood preserved in peat and sediment. The disruption to plant reproduction meant that even after the aerosol veil began to clear, the seed banks needed for forest recovery had been partially depleted, extending the period of ecological impoverishment beyond the 6 years of maximum cooling. Tropical forests faced conditions their component species had no evolutionary adaptation to survive. Species that had never experienced sustained cold stress had no dormancy mechanisms. As temperatures dropped and light declined, they couldn't conserve energy by entering dormancy. Photosynthesis fell below the threshold needed to sustain cellular metabolism. Trees that had grown for centuries died within seasons, turning gray and skeletal under darkened skies. The forests didn't burn, they starved. The cascade moved up every trophic level. Herbivores whose food sources disappeared faced starvation. Megafauna with slow reproductive rates, elephants, rhinoceros, couldn't recover population losses quickly enough to sustain viable breeding groups. Predators died as prey density dropped below the threshold needed to sustain carnivore metabolism. The collapse wasn't simultaneous everywhere. Regions with oceanic buffering or altitude-modified microclimates maintained marginally better conditions for longer. But the direction was uniform across every continental interior and tropical zone. Human groups that had survived the immediate ash burial now faced a planet where even uncontaminated landscapes offered almost nothing edible. Hunting became unproductive as prey populations collapsed. Plant foods failed as vegetation died across entire regions. The groups with access to coastlines had a partial buffer, marine ecosystems, insulated by oceanic thermal mass, degraded more slowly than terrestrial ones. Fish, shellfish, and marine mammals persisted in shallow coastal waters when inland food chains had failed entirely. This coastal access likely determined which human groups survived long enough for the stratosphere to clear and ecosystems to begin recovering, a recovery process measured not in months but in decades. The archaeological record around 74,000 years ago goes sparse abruptly, not gradually. Sites across South and Southeast Asia that had shown continuous occupation for tens of thousands of years stopped producing evidence. Tool assemblages disappear. Fire pits go cold. Middens, the archaeological trash heaps of bone, discarded tools, and food waste, end at the ash layer and don't resume for millennia. The silence extends even to areas that received only light ashfall, where burial wasn't the cause. The problem was something more fundamental, the collapse of conditions necessary to sustain human life. The record doesn't go completely silent everywhere. Sites in East Africa, cave systems along the southern coast, rock shelters in the Rift Valley show continuous or near-continuous occupation through the Toba eruption period. The tool technologies continue. Evidence of fire, food processing, and symbolic behavior like ochre use persists. These weren't large populations. Artifact density suggests groups numbering in the dozens per site, but they persisted when populations across Asia did not. Genetic evidence explains why the East African record continued when populations elsewhere collapsed. The human genome carries the record of every population contraction our ancestors survived, embedded in patterns of DNA diversity visible today. Mitochondrial DNA, passed exclusively through maternal lines, and Y chromosome sequences, transmitted from fathers to sons, both show signatures of severe population contraction between 70 and 80,000 years ago. The signature appears as a dramatic reduction in genetic diversity across billions of living people. All mitochondrial lineages trace back to a relatively small number of ancestral sequences, with a visible convergence point around the Toba eruption period. Population geneticists measure this through a statistic called nucleotide diversity, the average number of genetic differences between two randomly selected individuals in a population. High diversity indicates a large, stable population that has accumulated variation over many generations. Low diversity indicates a recent bottleneck, a period when population size contracted severely enough that most lineages died out, leaving only the descendants of survivors to carry forward into subsequent generations. Human nucleotide diversity is low relative to other great apes. Chimpanzees, with a fraction of the human population, carry significantly more mitochondrial DNA diversity than all 8 billion living humans combined. Gorillas do too. This is the genetic bottleneck made visible, the evidence that at some point in the past, the human population contracted to a size small enough to erase most of its accumulated genetic variation. The estimates of minimum effective breeding population that would produce the observed diversity range from roughly 3,000 to 10,000 individuals, depending on methodology. All point to the same period. All point to the same order of magnitude of loss. The convergence of genetic and archaeological evidence points toward East Africa as the primary refugium. Coastal and near-coastal environments offered specific advantages. Marine food sources buffered against terrestrial ecosystem collapse, and oceanic thermal mass moderated temperature swings more than continental interiors. The groups in East African coastal refugia weren't selected for any particular genetic or behavioral advantage. They were positioned where the intersection of marine resources, moderate temperatures, and lower ash deposition kept the food web functional when it failed almost everywhere else. When the stratospheric aerosol layer eventually cleared, as ice core sulfate concentrations show it did, gradually declining over approximately 6 years, sunlight returned, temperatures stabilized, and vegetation began recovering from seed banks that had persisted through the volcanic winter. The recovery was slow. Tropical forests take decades to re-establish canopy. Animal populations recovering from near extinction require multiple generations before reaching densities that support sustained human hunting. The small surviving human groups expanded into a landscape that was ecologically simpler than the one that had existed before the eruption. Many megafauna species had not recovered, and the mosaic of diverse ecosystems that had supported larger pre-Toba populations was only partially restored. What those survivors carried was not just their lives. They carried the entire knowledge base of Middle Stone Age technology, the tool-making traditions, fire management, food processing techniques, and social coordination that had developed over the preceding tens of thousands of years. Everything that came after, every subsequent development in human technology, language, and culture, built on the foundation preserved in the cognitive and behavioral repertoire of the few thousand individuals who made it through the volcanic winter. The genetic bottleneck is not just a record of near extinction, it is the record of exactly how narrow the thread was through which everything that followed had to pass. Lake Toba today is peaceful. Tourists swim in water 900 meters above sea level, boat across its 100-kilometer length, and photograph sunsets from resorts built along the crater rim. Most don't know they're floating inside the scar that nearly ended the human species. Beneath the lake, the magma chamber refills, slowly, over timescales measured in hundreds of thousands of years. Small earthquakes register continuously. Hot springs vent gases along the shoreline. The pressure builds as it always has, indifferent to the 8 billion descendants of the few thousand who survived the last time it released. The geological intervals between Toba's eruptions are measured in hundreds of millennia. That's not reassurance. It's arithmetic. The prior eruptions happened 840,000 and 501,000 years ago. The last one was 74,000 years ago. The cycle hasn't ended, it's in progress.